Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another interesting presentation topic. And this time, the topic is understanding one-line drawings for a power system network. This is such an important topic uh, based on as a development engineer, as an experienced engineer, for you to know how to read one-line drawings, because that is the basis of you basically progressing into your career, especially in power systems area. My good name is John Kweko Amotu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Okay, so let's talk about the outline for my presentation. And the first thing we'll talk about is what is a one-line diagram. A one-line diagram is basically the simplest representation of the power system network for a facility, for a substation, or for a generation facility. And it is represented by connections, nodes, and buses, and has a lot of symbols on it, basically, that interprets what those symbols means. Next, we'll talk about all the equipment that are part of a one-line diagram. You know, what equipment basically consist of the whole composition of a one-line diagram. Then we'll talk about different one-line diagrams, basically starting from the generation point. You know, so we'll talk about a one-line diagram for a generation facility, a generation plant. Then we'll move on to a one-line diagram for a medium voltage switchgear. And the next presentation basically will consist of one-line diagrams on the low voltage end. So we'll basically step down to voltages of about 600 volts AC, and all the way up to 480 volts AC. Then I'll create another presentation that will basically be how to read three-line diagrams. So on the three-line diagrams, we'll start from the generation point, and basically up to the substation, and from the substation up to the medium voltage level. Then scale back to low voltage level. Then I'll do a last presentation, which is basically how to read wiring diagrams that pertains to generation facility, medium voltage facility, low voltage facility. Okay, so now let's talk about components of a one-line diagram. You know, like I indicated, a one-line diagram is basically the simplest representation of all the components that are integrated in for a generation facility, for a transmission facility, or for a medium voltage facility or low voltage facility, right? Okay, so and also it has symbols basically that explains what those equipments or those representations mean, you know. And as a development engineer, as an experienced engineer, as a young engineer that is about to start your career, this is one of the most important pieces if you are working in the area of power systems engineering, for you to understand. You know, if you understand how to read one-line diagrams, and matter of fact, beyond that, how to draw one-line diagram from scratch, right, without utilizing modeling software, right, that itself is a plus for you, right, because that is the basis of you as a power system engineer, for you to read one-line diagrams, draw one-line diagrams, update one-line diagrams, right? That is basically, you know, your plus, right? Because there are many engineers out there, experienced engineers out there, that don't know how to read one-line diagrams, and you'll be baffled by that. Yeah, it is there, because if you know how to read one-line diagrams, if you understand how to read one-line diagrams, right, it helps you to basically develop your career, right? If there should be any problem in the field, that itself is the basis, you know, for you to be able to investigate and find solutions to the problem. So it is very important for you to understand how to read one-line diagram as a development engineer, experienced engineer, and as a supporting engineer, during construction times, for you to understand how to read one-line diagrams. Okay, so the first thing is that I need to talk about as part of the components of a one-line diagrams is it consists of a utility feed section, right? So basically it has a switch yard, right? That has basically many equipments, and the switch yard connection or substation connection is represented by this symbol, right? Okay. If you are utilizing a modeling software, right? On the other hand, it can be represented by many configurations of substation bus layout. We have a different bus layout, right? We have the ring bus, we have the breaker and a half, we have a double bus and double breaker, okay. So then we have a single bus. Then we have a double bus with a sectionalizer, right? That is two buses with a tiebreaker in between it. So the tiebreaker is called a sectionalizer, right? Okay, so these are all the different bus schemes that we have out there that basically can be shown on a one-line diagram. Next is a generator, right? Okay, so a generator represented by this symbol. Then the neutral, the type of grounding that it has, right? It can have a impedance grounded, which can be, or resistance grounded, which can be medium, low resistance, and high impedance, right? And the high impedance, basically, a distribution transformer is utilized for the high impedance grounding of generators, right? So on a one-line diagram, you can have a generator represented by this symbol, right? Okay, then you can have a transformer, right? Okay, so at the terminal of the generator, if let's say you have 13.8 kV as your terminal voltage, or 18 kV as your terminal voltage, or 23 kV as your terminal voltage, there is a step-up transformer, right? That steps the voltage, let's say, to 115 kV, 230 kV, or 345 kV transmission level voltage, right? Okay, so this side of the transformer will be wound in the delta, and this side will be wound in the Y ground. Okay, then you have switch gears, right? Okay, so there's something they call auxiliary bus, right? Okay, so if you have a 30.8 kV, 18 kV, 23 kV, right, there is a step-down transformer that is called an auxiliary transformer, right? That steps the voltage down 18 kV, that steps it down to, let's say, 4.16 kV, right? To be used by a switchgear, right? And that switchgear has many loads, right? Has many loads. And there are so many configurations of the medium voltage switchgear. We have a double bus with a tiebreaker in it, or a single bus that basically, based on criticality of the load. Then you can have a battery systems, right? Okay, so battery systems basically, is the DC part of the one line. Basically, it provides DC voltage to all the critical equipment, to include relays, annunciators. All these equipment basically, devices utilizes DC voltage. Right? Then you have a battery charger, right? So the battery charger is basically there to keep the DC voltage on the battery systems, as the DC battery systems charged, and to keep the voltage constant, and at the same time help provide the required critical voltage to all these critical devices that is needed, in a generation facility or a transmission and distribution substation. Okay, so I made mention about what is a one-line diagram, and basically it's a single line that is a simplified representation of the electrical system, and it has many nodes and connections and also symbols, right? And there are so many benefits that is tied to one-line diagrams. First of all, it helps us to be able to plan for maintenance of the equipment. Then also, if there's a future modification, right, having that baseline one-line diagram helps us to plan for any modifications that we have. And also, if there should be a power interruption, having knowledge of the one-line diagrams helps you to identify and helps you to perform your investigation. So these are, just a few of the benefits of a one-line diagram. Okay, so now let's talk about, let's pivot on a typical one-line diagram for a generation facility, right? Okay, so, and this one, it's basically a one-line diagram for a generation facility, right? So as you can see over here, this is the generator, right? And basically its goal is basically to generate the required power, to be stepped up to the grid, right? Okay, so sometimes for a generator, you can have a generator breaker, right at the terminal of the generator before it goes to a step-up transformer. It's all based on the different the configuration of the generation facility. Sometimes too, you can have a unit connected generator, right, where you don't have a generator breaker. Then right from the generator, it gets connected to a step-up transformer that steps the voltage up from, let's say, 13.8 kV, 18 kV, 23 kV to a transmission level voltage. You can have 115 kV. And for this instance, you have a 230 kV transmission level voltage, right? As you can see over here. So it goes to a switchyard that has a nominal voltage level of 230 kV, right? 230 kV. So within this switchyard environment or confines, you have different bus configurations, right? One of them is a breaker and a half scheme. You have a ring bus, right? You have a double bus and double breaker, right? For that voltage level, these are the type of bus schemes that are applicable at that voltage level, right? Because the single bus scheme is applicable to a medium voltage level, and the double bus with a double break with a sectionalizer is applicable to the medium voltage voltage level. So for a generation facility, right, there's something they call auxiliary power, right? Okay, so what this auxiliary power does is it provides power to all the supporting equipment that helps with the generation of electric power, right? These are all the supporting equipment, right? You have motors, valves, and for valves, we have different valves, right? Air operating valves, motor operating valves, and just to name a few, right? Okay, so for motors, you can have a condensate pump motor, right? And what does it do? It basically takes the water from the condenser, right? The steam that basically comes from the low pressure end of the turbine, right? Then once it gets into the condenser, it collapses because of it has a high saturation content, right? And also it comes into contact with cold water that is flowing through the walls of the condenser. So basically it collapses and basically forms water condensate, right? So if it forms the water condensate, you need a pump motor scheme to pump the water to the next level as part of the cycle, right? Because you're pumping the water towards the boiler, right? Okay, so once the condensate pump motor pumps the water, then it goes to the boiler feed pump. So the goal of the boiler feed pump is to pump the water it receives from the condensate pump to the boiler, right? For all the boiling, all the heating system, the boiler basically burns whatever, if it burns coal, basically you have water, that same water that flows through the walls of the boiler, basically then it gets turned into steam. Then the cycle repeats itself, right? In between, as part of the improvement of the efficiency of the cycle, right? You have a feeder heat extraction piping, right? That have different motors, right? And pumps, right? So basically, it extracts the steam that basically gets get impinged on the turbine, right? So it utilizes that amount of steam to basically heat the feed water system before it gets to the boiler. This is part of basically the efficiency. You're trying to improve the efficiency and basically extracting heat from the steam that is already flowing into the turbine, right? To warm up this feed water heater that is basically going to go to the boiler. So you have a different motors, like I indicated, different valves and all these equipment that are part of the power plant schemes, right? So you need to provide power for it, right? So that is what this auxiliary power system or auxiliary system basically entails. So you have a 3-winding transformer, right? You are coming here with 13.8 kV or 18 kV. Then you're stepping it down to, let's say, 4.16 kV as 2 secondary windings, right? Basically, because the goal is basically to utilize one transformer, a 3-winding transformer, to be able to multiply the secondary voltages. So that is why you are utilizing a 3-winding transformer, to be able to achieve different many medium voltage buses that can provide power, right? So you are able to step the voltage down utilizing this 3-winding transformer to 4.16 kV and achieve many medium voltage buses out of that. That is going to provide power to motors that are rated at 4.16 kV. Then from there, you have a 4.16 kV, right? Bus schemes, right? So the next goal is to be able to step the voltage down from 4.16 kV to, let's say, 480 volts, right? To achieve a motor control center, right? So you have a motor control center buses, many of them, right? That provide power to all these motor operated valves, air operated valves, and many more, right? So that is what all this auxiliary power looks like. Okay, then if you want to start up a generation facility, right? The turbine generator is at standstill, right? It is not rotating. It is not generating any power. So to start the generation facility, you need to use a startup power. So that itself comes from the grid, right? So that grid is separate from this one, right? This one is the one that is tied to the generation facility, right? But if you want to start generating power, you need to provide electrical power to your auxiliary equipment. So you can have a 115 kV scheme transmission line that comes in, 230 kV transmission line that comes in. Then you have a station service transformer that steps down the voltage from 115 kV or 230 kV to a medium voltage level, let's say 4.16 kV or 6.9 kV, to be able to provide that separate auxiliary power to all these equipment, motors, valves, etc., that are in the generation facility, to be able to start up the generator, right? Because, think about it. The generator needs a lube oil, right? You have a lube oil motor. You have a lube oil pump, right? You need to provide all this power to these motors. You have a condensate pump motor. You need to provide power to it. You have a boiler feed pump motor. you need to provide power to it. So to start up the generation facility, you have a station service transformer that is dedicated to a separate transmission network that provides this power. At the same time, there should be a backup supply if, let's say, you should lose this transmission line. So you have diesel generators, about 2-3 of them that are located in the generation facilities, right? So that has the capability, if you should lose that dedicated source to start up the plant, then it goes through an automatic throwover switch, and basically is able to start up the generators, the standby generators or emergency generators, to be able to continue to provide that auxiliary power to all this equipment that helps the generator to be able to turn on and start generating power. Okay, so now let's talk about the medium voltage one line diagram, right? Okay. So I indicated that for a generation facility, right, we have a medium voltage buses, switch gears, right, that you need to provide power to. That provides power to motors, large motors, right? Then from this medium voltage switch here, it gets fed to other step-down transformers that steps the voltage down from, let's say, 7.2 kV to, let's say, 480 volts to motor control centers, right? That provides power to all other auxiliaries, air operating valves, motor operating valves, etc., right? Okay, so you have a generator, right? Okay. And you have a step-up transformer, right? That steps the generator voltage, let's say, from 18 kV to 230 kV, right? Okay. So right at this top is your feed to your auxiliary bus, right? To your medium voltage level, right? So it goes through a 3-winding transformer, right? That steps the voltage down from, let's say, 18 kV to, let's say, 4.16 kV or 7.2 kV to achieve that medium voltage bus, right? Okay, so you are coming in. This is the feed, the incomer. They call this one the incomer, right? Okay, so this is the incomer breaker. So you are coming in as part of the design of the medium voltage switchgear. You need a breaker to interface with the bus. This is what they call the bus, right? That is rated at 7.2 kV, right? Then you have a tie breaker, right? You have a bus here. You have another bus here, right? You need a tie breaker. You know, this is part of a redundancy that has been built into this switchgear, so that you have 2 feeds that come into independent feeds that come into this switchgear, right? So you have a feed that comes like this, right? From a different step down transformer, right? Then another feed comes in here from a different step down transformer. So that is how the redundancy and reliability is built when you're designing switchgears. Okay, so over here is all the protected relay schemes that are part of these switchgear, medium voltage switchgear. So as you can see over here, you can have under voltage relays, over voltage relays, timers, 62, right? That basically helps, in terms of, transferring of power and voltage from one bus to another bus, right? Based on detection of the voltage, if there should be an under voltage condition on one bus, and so that you can basically trip this breaker and close this tie breaker first, then trip this incomer breaker, so to be able to transfer all the loads onto this bus. Okay, so over here are all the relays that are tied to this section of the bus, right? Like I told you, you have a double bus with a tie breaker in between, right? Okay, you have an incomer that is coming here. You have an incomer that is coming here, right? Then you have outgoing feeders, outgoing feeders, outgoing feeders, outgoing feeders, right? And these are all breakers, right? So these are all the breakers that you see over here, right? And one of them is an incomer, right? Remember, I told you that, based on reliability, based on the goal, that goal to achieve redundancy, you have independent, power feeds onto these bars. That is, the power feed to these bars is from a dedicated, is from a different source compared to the incomer feed that is coming over here. Okay, so these are the feeds that provides power to all the large motors and transformer feeds to basically step the voltage down from 7.2 kV to, let's say, 480 volts level, right, to achieve a motor control center, right, where you will have a motor control center that provides also you have breakers that you can use to provide power to motor operated valves and air operated valves, right? Okay, so these are all the relays that basically is used to protect this feeder, right? These are all the relays. So a lot of the relays you see over here are 50 phase instantaneous and phase time over current relays, right? Then you can have a zero sequence relay that is detecting ground faults, right? 50N and 51N, right? So you should be able to detect phase faults, that is phase instantaneous, phase time over current. Then also you should have a sensitive CTs that should be able to detect ground fault, because ground faults are sometimes the fault current is so small so that you utilize a flux summation relay or zero sequence relay to be able to detect that amount of small fault current to provide that sensitive fault detection, right? Okay, so these are all ground fault detection 50G. 50G means it's instantaneous ground fault detection. That is all on this feeder, right? And these are the phase instantaneous, phase time over current protection that is shown on all these outgoing feeder. Okay. So this is the unit, the incomer that comes to this bus, right? So this is an incomer that comes in. So all these breakers, right, as you can see, these breakers are rated at 1200 amps, and the incomer is rated at 2000 amps. So that is a typical standard how these breakers are rated, right? Okay, so usually in rating of these breakers, load is built up, and after that is system settings is performed, right? Okay, so they perform the load flow, short circuit analysis, right? Motor starting analysis, right? So that's how they come up with all these designs, right? Okay, so the load flow is basically to determine the voltage profile, right, across all buses and connected equipment, right, and also to determine the need for if there's the need to install capacitors, right, to basically boost up the voltages after that. Then also to determine the capability of the equipment to basically withstand continuous current rating of the equipment and the voltage rating of the equipment. Then you also perform short circuit analysis, right, to determine the withstand of the equipment, right, based on its short circuit capability, right. So that is how the bus ratings are determined, right. So the bus has a continuous current rating, nominal voltage rating, then a short circuit capability, right. The short circuit capability is based on symmetrical rating and asymmetrical rating, right. So these are all determined based on system studies. Okay, so now let's talk about another medium voltage one-line diagram, and this time is a 4.16 kV instead of the previous slide we talked about a 7.2 kV switchgear, right? But this time we're talking about 4.16 kV switchgear, right? As an auxiliary bus, right? And I made mention that the goal of this bus is to provide support to auxiliary loads that are part of the generation facility. But on a transmission and distribution level, right, its goal is to provide, basically, you achieve all these medium voltage buses and switchgears to be able to provide load, power, and voltage to your loads, to your customers, right? Okay, so as you can see over here, 4.16 kV. So that is your nominal voltage of the switchgear. And over here, you can see 2000 amps. So that is your continuous current rating of the switchgear. Then you can see over here 350 MVA. That is your short circuit capability of the bus of the switchgear, right? Okay, so the 350 MVA is an older system of rating for these switchgears, right? But the newer ones are basically, you see that the rating is shown as 21 kA, right? 31 kA, 40 kA, right? 63 kA, right? Okay, so the 350 MVA is basically, a combination of, root 3 times V times I, right? So your short circuit current and your short circuit voltage, the short circuit current times your nominal voltage and root 3. So that is how they are able to achieve the 350 MVA, right? Okay, so it's all basically the same, right? Okay, the newer switchgear it's basically shown in kilo ohms, right? Okay, so like I indicated, this is a double-ended switchgear, right? So basically it has two buses, right? One bus here and another bus here, right? Okay, so these are all your loads that goes to a motor, right? As you can see over here, these are the horsepower rating of the motor: 900 horsepower, 900 horsepower, 400 horsepower, 400 horsepower, 400 horsepower, 450 horsepower, 400 horsepower. So, like I indicated, and I'm emphasizing, right, the goal of this switchgears, auxiliary switchgears, is to provide power and voltage to all the auxiliary loads, which includes motors, etc., right, in the power plant. So, you have an incomer, right? And on this switchgear, you have an incomer that comes in, right? Then basically provides power to this bus, right? And this bus is tied to this bus, right? Okay, so same thing. This one, you have an incomer that basically is fed from a dedicated source. And this one, the incomer that is coming here to power this bus is also coming from a dedicated source, different from the other bus. The goal is basically to create a redundancy, right? So that if you should lose a feed to this bus, right? This bus will be there, and you'll be able to trip this bus and basically close the tiebreaker, right? And to keep your loads basically, being powered, right? Okay, so on the right-hand side is a legend, that shows a naming convention for different types of loads. So one of the important things that you want to take a look at if you are learning how to read one-line diagrams or draw one-line diagram is to be able to look at these legends and its description over here. Very, very important. That's how you learn, and you build up, how your capability to be able to draw one line and be able to understand and read one-line diagrams, right? Okay, so over here are all the relaying schemes, okay, that you can see, as you can see over here. Like I told you that you have a 5051 for your phase protection, then a zero sequencer component that is 50G for ground fault protection, right? Okay, so with that comes to the end of my presentation, and if you like this presentation, don't forget to select the like button in YouTube and select subscribe. There are many channels there of basically a lot of presentation learning channels and learning presentation for your career, to develop your career. Okay, with that, that comes to the end of my presentation. Thank you so much for your listening. Yes, thank you.